So, hello everyone, I'm Yerod Anas. I'm a research engineer at University of Liège. I will be presenting my master thesis for the Geospatial Awards 2023, titled 3D Modeling of Road Infrastructure based on CTGML 3.0 and its CTGs in encoding, and supervised by Professor Hajira Fiqa and Dr. Nisjin Antoine. Let's start by defining urban digital twins. So urban digital twins are virtual representations of cities and urban landscapes, and the technological backbone of these digital twins are 3D city models that represent different city objects like buildings and transportation networks, including also road networks. So the main OGC standards for 3D city models are CTGML and CTGSN. CTGML is a conceptual model and exchange format that standardizes the representation, storage, and exchange of these models. And CTGSN is a JSON encoding of CTGML, which is more lightweight, compact, and user-friendly for developer. So we are interested in the transportation model of CTGML 3.0, and in this figure we are showing the UML model that shows the different classes for the transportation model, and the transportation model is the model for roads and railways and other transportation networks. In this case, it's roads. So in this figure, we are showing the model that is represented in the CTGML 3D city model, and as you can see, the road is represented by different surfaces or areas. They can be traffic areas like lanes, or auxiliary traffic areas like median strip or vegetation, and we have also the traffic space in above all that. So the research question is how to produce these models based on CTGML 3.0 standard and its CGGs and encoding, and we have two contributions. So systematic approach for creating geometrically consistent 3D road models in CTGs and format, and also an optimized method for storing and visualization of these models. So the method consists of three steps. First, the data acquisition. So we collect the 3D road data using a mobile mapping system, and after that we process this data to transform the raw data into a 3D road model that should be that can be stored in a database. In this case, it's a MongoDB database, and uploaded to a web application for visualization. So for the data acquisition, we are using a mobile mapping system that is accompanied also by GNSS and IMU observations for georeferencing the 3D point cloud, and also images to colorize the point cloud. So in the output, we have the 3D point cloud with RGB values and the textures. So for the data processing, we have 4 sub-steps: cleaning to filter the noise, and after that we use the results to create a digital terrain model that will be used to extract the linear structure of the road, and after that we will codify each line with a unique code for the 3D modeling process. So the codification is basically based on the nature of the line and also each section. So for example, the first section is S1, and the line could be, for example, here trottoir in French, and it's sidewalk. So the next step is to transform this linear structure in a 3D road model, and we are using a spatial ETL process to do this. The software is FME, so we are using the linear structure and the textures to add the visual details of the road to the 3D model, and the output is a CTGSN file. The process is more complex than what we are showing here in this slide, but basically the first step is to separate different sections, intersections and roundabouts, and after that different surfaces for separate 3D modeling, and after that we combine the linear features of each surface and close them to create multi-surface geometry. So here we show the result with the textures, and as you can see, we have different surfaces. We have traffic areas which are sidewalks and roadways, and auxiliary traffic areas that are the median strip or the vegetation. The next step in the process is the validation, and we start with the schema validation. Data schema compliance: is the file syntax correct? And here we are using a CGVal tool to ensure that the CTGSN is correct. The CTGSN schemas are respected, and if it's not the case, we need to apply a patch to make some changes to the syntax. The next step is the geometry and topology validation, and here we are looking for geometric and topological errors in the model itself and not in the file. and we are using Flood 3D as an ISO 19017 compliant geometry validator that gives us different geometry errors for different geometry types as shown in the figure. So for our method, the possible geometry topology errors are twofold. We have the non-planarity errors as shown in the right figure, and we have also the self-intersection errors or auto-intersection errors, basically when a polygon intersects itself, and these errors can lead to false outcomes of analysis. So we need to correct these errors. First, for the self-intersection, we can in the modeling process calculate the intersections and create vertices wherever an intersection occurs. And for non-planarity, we can either do a triangulation. Triangles are basically planar, or we can drop the geometry on a planar surface. After that, we need to load the data in a database, and we use Measure 3D, which is a MERN application for CTGs and files management using a RESTful API, and it uploads the files into a MongoDB database, and after that we can visualize the results in the client layer, and we added support to semantic surfaces. As you can see in this figure, we can select one surface within one section, and we can have all the attributes about this surface. In this case, it's a traffic area in a roundabout, and we have other information like the surface material here is asphalt and other attributes. So the results, we can say that we developed a semi-automatic approach for systematic modeling while ensuring consistency and accuracy, and and also we ensure that the models should be integrated in 3D databases. The work was also presented in the Geospatial Week in ISPRS, and it should be published soon in the ISPRS archives. Thank you, and if you have any questions. Thank you so much.